Okay guys, this is a vodcast on part 3 of the application SAC, the tech-able part. Stay tuned. Right, so this SAC began with 12 multiple choice questions. The first few were designed to be relatively routine and straightforward. I think most of you got this one right. So there's vector A plus 2 lots of B, you need to find B. So obviously you take that expression for A plus 2B, is subtract A from it, divided by 2, and voila, you get your answer. So there, I'd be surprised if you didn't get that one correct. All right, moving on to the next one. So we're dealing with a inverse cos function, and this is again one of those standard sort of question 1 type questions you might get on exam 2 at the end of the year. You have to state its maximal domain and or range. In this case, you need to state both. So where do you go to for your maximal domain? Of course, you focus on the argument of the function. You set that from -1 up to 1 inclusive. You solve for that inequation. You get values 0 to 1. So obviously anything not 0 to 1 is ruled out. And what drives the range? Of course, your dilation from the x-axis and your vertical translation factors. So normally goes from 0 to pi, the dilation of 2 makes it go from 0 to 2 pi, and then everything shifts upwards by pi, giving A as your answer. All right, question 3 was a straightforward question. If you know your rule for the dot product is equal to magnitude of A, magnitude of B times cos theta, rearranged to make cos theta the subject. This should have proved no problems at all. So dot product, multiplying your I, J's and K's, and divided by the two magnitudes, really a straightforward question, I would have hoped. Okay, moving on to question 4. However, that wasn't a straightforward question. Let's have a read of it. So you might see it from the solutions, but let's have a read. The angle between A and A plus B is 30 degrees. Now we're told the magnitude of A and the magnitude of B are equal. Therefore, that triangle that you see to your right is an isosceles triangle. So the angle at the other acute angle is 130 degrees, making it 120 degrees is the third internal angle. However, when we calculate the dot product, of course, this is what the intended test was all about, is it's all about it's calculated tail to tail. And in that diagram, vector A and vector B are not currently tail to tail, they're head to tail. So when you do move them tail to tail, you're dealing with 60 degrees, not 120 degrees is the angle between them. Therefore, when you go and apply the dot product rule, let me just grab a color. Okay, that's what you're dealing with. Now, A and B are equal. The magnitude of A and B are equal. Therefore, magnitude of A times magnitude of B could be written in any one of those two ways. Magnitude of A squared, magnitude of B squared, or something equivalent. And of course, something equivalent to magnitude of A squared is A dot A. And that's what you see there in part E. A little bit sneaky, a lot of you messed that one up. All right, so there weren't too many easy questions left in the multiple choice thereafter. Okay, have a look at this. The asymptotes of the graph y equals pi times the reciprocal function of the inverse tan function. All right, so let's get our heads around this. So here's our inverse tan function. Let's just complete it. So two horizontal asymptotes looking like so. But what we're not doing is looking at that graph, we're looking at its reciprocal. So the horizontal asymptotes remain horizontal asymptotes, but their values become reciprocated. So that's why we move on to this picture over here. You've got two horizontal asymptotes still, positive and negative, but the reciprocal of pi on 2 and minus pi on 2. All right, that's great. After that, of course, it's been dilated by a factor of pi from the x-axis. So those asymptotes move to plus or minus 2. Okay, so y equals 2, y equals -2. The graph is above those two asymptotes, as you can see. So, and of course, if you think back to the original graph, as you get closer and closer to x equals 0 from the left or the right, you're approaching a y value of 0. Of course, zeros or roots of functions, once you reciprocate them, become vertical asymptotes as well. And so you've got a picture looking like that and like that. Okay. Now, I guess you could have pulled out your CAS, but there was no real need to. Okay, so just going through it one more time, recalling what inverse tan looks like, or arctan. Reciprocating it means our horizontal asymptotes, their values remain horizontal asymptotes, but their values are reciprocated. You apply a dilation of pi from the x-axis, making them plus or minus 2. But of course, don't forget, it's not just plus or minus 2, it's plus or minus 2 with x equals 0. All right, good. Hopefully that was okay. Not done overly well, but I guess it was a fairly challenging sort of a problem. All right, so what about this one? Okay, so they're all sec or cosec options except for the one sec option. So it's more natural to think of it as a cosec graph, because we know cosec graphs have a vertical asymptote at x equals 0. All right, so now let's start to look at the values themselves. Okay, so we know it's got a period. It's going through one full cycle every 2a, so we can calculate the coefficient of x we can expect in the argument. So anything that doesn't have a coefficient of pi on a, we can immediately remove. Okay, just down to those two options. Let's see what other details are here. So it goes to the y coordinate of the local minimum is 2a. The y coordinate of the local maximum is 0. We know that the vertical translation factor will always be the average of those two. So the average of those two is a. So it must be d. Okay. So just there's a real routine to those sort of questions. Just piece it out part by part. And obviously sec isn't the option. Okay, good. Okay, question 7. A particle at P at a random point on the unit circle is moving in an anti-clockwise direction, where x and y are the horizontal and vertical positions of the particle in centimeters from the origin. So there's a nice little picture. It's just the unit circle, and of course it's moving in that positive direction. So as theta is increasing, that's the natural way we think of positive changes in theta as an anti-clockwise movement or rotation around the unit circle. Okay, P completes one full revolution every second. P completes one full revolution every second. We know one full revolution, it's the unit circle after all, so that's got a radian value of 2 pi. So the distance or the changes in theta every second would be 2 pi on 1, or simply 2 pi radians per second. So every second it goes through a cycle, a full cycle. In other words, in terms of radians, 2 pi changes in radians every second. Fantastic. Now, if theta is the angle OP makes with the positive x-axis, that's all good. Then what are we going to do? Okay, we need to calculate d theta dt. So d theta dt is there. So we're looking at anything that's not 2 pi has to go. So we've got 3 options there. But we also need to work out the changes in x with respect to time. And this is the one related rates question on across all papers. In fact, there'll be more of it on your next SAC, but there was one little token related rates, and this was it. So what is x after all? X is equivalent to cos theta. So dx d theta is minus sine theta. We match the two together and we get an expression for dx dt, and it's going to be equal to minus 2 pi sine theta. All right, question 8 was a little bit of a curly question. So if tan theta is equal to A, where theta is in the second quadrant, we know tan is negative in the second quadrant, therefore A is negative. That's something we'll bear in mind. Then tan theta on 2 will be what? Okay, first things first is we're relating an angle to an angle half the size, so we're going to bring in the double angle rule for tan, okay, and we're going to express tan theta on 2, or the subject, so I'm just making the subject of that equation y. So in fact, maybe it's confusing for you, but that's relating tan x to tan x on 2. So let's just think about y as being tan x on 2. So we resolve to make y the subject. So we're just making y as those replacements, y, and we get, lo and behold, a quadratic equation. Okay, so how do we solve quadratic equations? Easiest way, quadratic formula, and it drops down to this simple form. We've got two options. Now we know tan theta on 2 can't be ambiguous. It's got to be one or the other. Now, here's how to think your way through this. Okay, so theta was a second quadrant angle. Therefore, theta on 2 must be a first quadrant angle. So if I divide the domain, so here's the endpoints of the domain, divide each of those by 2, I can see clearly I'm dealing with a first quadrant angle. And we know tan must be positive in that first quadrant. Aha! So we need to choose the option that leads to a positive result. Now the trick is that A is not positive, which is what our natural tendency is to think of pronumerals. So that's why you really have to be on your game for this one. A is negative. So which of the two options will be the correct answer? Well, okay, let's go through it. So we need to realize that the square root, so this value, the square root of 1 plus a squared, is a value bigger than 1. So square root, of 1 plus a squared, is a value bigger than 1. So when we go minus 1 plus that, we've got a positive. So minus 1 plus 1 plus a squared is indeed positive. But if we take a positive and we divide it by a, which is a negative, we've got a negative. So it's not the positive out of the two quadratic options that we get, it's the negative. Hence, that must be your answer, not B. Okay, and that that was a little bit subtle, and a lot of you lost a mark there. All right, question 9, I thought was quite a nice little question. On the surface, it seemed like there was a lot of work to do, but actually, once you eliminated the first option, the others actually fell out almost automatically. I'll explain why. So you've got 3 points in 3D space. Which of the following is false? It's one of those negative questions that are always a little bit tricky. But okay, so let's just test the first one. So setting up an expression for AC is easy enough, and you can see almost immediately, AC and AB, and you can see the relationship between the two. AC will be twice AB, so obviously they're parallel, and they're also collinear. Collinear because there's a common point, A is involved. So straight away we can eliminate those two based on the fact that, well, one is the first direct up statement, and if the first statement is true, then obviously the second statement must also be true. Now, linked with the idea of A, B, and C being collinear, so if you can say AC is equal to 2 lots of AB, then remember we could go straight to our properties of collinearity. It must be the case that OC is a combination of 1 minus 2 OA plus 2 OB. Okay, and that comes directly from the collinearity property, but even if you don't remember it, that's totally fine. You can build it up as OC being equal to OA plus AC, okay, and then you can develop the same expression. So that gives us this expression, so you can see that's true, so we eliminate it. And of course, inbuilt in that kind of expression is the understanding if one vector is a multiple of the other two, then they're linearly dependent. So, and that leaves us with D. So the reason why D is false is because C is not the midpoint of AB, but rather B is the midpoint of AC. So that's how you do that one. Okay, a solution U to an equation of the form Z to the 4, the power of 4 is equal to A, where A is a complex number, appears in the complex plane. There it is. So let me just highlight that for you. It's of that classic form. That means there must be 4 solutions evenly spaced, in this case power of 4 by 90 degrees. So here's another solution, here's another solution, and here are my 4 solutions. So you can see they're separated by 90 degrees there, each of those 4 solutions, U being one of them. So V will be a solution to other than, so we're dealing, this could be V, so this could be V, that could be V, or that could be V. So there's 3 options for V other than U. Okay, so a possible location of V divided by 1 plus I. Okay, so this is all about really realizing, well, 1 plus I in polar form is just obviously the square root of 2, cis pi on 4. What's the geometric impact of dividing 2 complex numbers? Well, you're subtracting or taking the first complex number U in this particular case and rotating it clockwise this time rather than anti-clockwise by 45 degrees. Okay, now also, so that's what the cis part does. Let me just highlight that. That's what the cis part, it rotates 45 degrees clockwise because we're dividing, not anti-clockwise, as would be the case with multiplying. And the pi on 2 part means it'll be closer to origin. So pi on 2, which is 1.4, we're dividing by 1.4, multiplying by about 0.7. So this V divided by 1 plus I must be one of these 3 options here, which I'll highlight, one of those 3 options that has been moved 45 degrees. So moved obviously onto one of the axes and then brought closer to the origin. So you can see B is on the axis, so that could have been that as an option, but it's further away from the origin than U. A is not on the axis, E is not on the axis, C is on the axis, and it is closer to the origin, so it's meeting the brief. So it was this must have been our V over here. That was the only candidate for V. It's been rotated 45 degrees clockwise and moves closer to the origin. So hopefully that makes sense. Okay, guys, so here's a question different from, but very similar to one that appeared in your textbook. Now, the reason why I included this on the SAC was because I had not a single student approach me about how to do these questions, and which is quite different to past years. And I thought, let's see if they really know what they're doing then. And sure enough, most of you didn't. So please, the students that have had success in this subject are the ones that really do follow up all those questions they have encountered from the textbook and dot all their I's and cross all their T's. So really, if you didn't know how to do this one, then it probably meant you didn't know how to do it when it came to encountering it in the textbook, or you just looked at solutions, were happy with that. But you've got to aim to get these right. Okay, so leave no stone unturned in your attempts to master this course. Okay, good. All right, so let's have a look. So we're told cosec of some angle beta is equal to the value b. We're told beta is in the 3rd quadrant. So we've got to find 2 values that satisfy sec of x equals b equals the same value over an interval from 0 to 2 pi. So there was very similar questions to go to in your textbook about this. So the first thing to realize is we're switching from a fact about cosec, reciprocal sine, to a fact about sec, reciprocal cos. So straight away, that's a bit of a no-brainer to say, bring in your complementary properties, okay? And the way I always remember is just linking it back to the unit circle over there. There it is. Now it's not about cos and sine, but the same complementary properties apply for sec and cosec. So the same deal applies. Now what we're going to do is find theta, an expression for theta that satisfies this. So that string of statements, they're all true, is equal to beta. So we need to work backwards and find out what theta can be in terms of beta. So let's go and see the next level of this. Okay, so what we need to do is of course we're linking sec to cosec, and we know that cosec of beta is equal to b. So we're going to use that knowledge over here. So we're going to assign the argument of that function equal to b to find one possible value of theta that satisfies sec x equals b. And here's the other argument. We're going to assign that to beta as well, and get a second expression for beta. So here are two distinct values of x, that satisfy sec x equals to b, lowercase b, pi on 2 minus beta, and beta minus pi on 2. Now why don't those options appear? And it's because we need to find solutions over the interval from 0 to 2 pi. Now the period of the sec function is equal to 2 pi. So it's from there, it's simply a case of adding 2 pi if it's below the domain of 0, or subtracting 2 pi if it's above the domain. So, okay, looking at the first one, you can see, so this one over here, you can see that's a value, a negative value. So we need to add 2 pi onto it to bring it into the required domain. And the second one is beta minus pi on 2, and that's perfectly fine. That's inside the required domain. So then we can bring about our two solutions. So here's one solution. Let's just go back. Here's one solution. So it's pi on 2 minus beta was the angle, but it was a negative one because beta is a third quadrant angle, and then we just added 2 pi to it to get one solution, and beta minus pi on 2 was fine. That was in our domain of 0 to 2 pi. So there's our two solutions, leading to option E. All right, now there's another way you could have gone about it. So I'll just canvas. So we could have just made sec the subject, cosec the subject in terms of sec. So there's the rules linking cosec to sec. So obviously sec pi on 2 and sec minus pi. So that's where we're keeping a positive value. So pi on 2 minus theta and minus pi on 2 plus theta. We know that cosec of beta is equal to those. If I replace theta with beta in each of those cases, so there's something true that comes from the complementary properties, this time working with the cosec, the subject. Now I'm just going to say theta equals beta, and we're going to make all those statements and then equate them equal to b. And then from there I can get my two solutions, pi on 2 minus beta and minus pi on 2 plus beta. And then we get back into the same scenario. Pi on 2 minus beta is outside the domain. Adding 2 pi to it gets us inside the domain, option E. There is, if you don't like that way to think about these problems, here is a third. And this is, I would say, the toughest, but that's picturing what's going on here. All right, so beta is this third quadrant angle. Okay, there it is, taking us into the third quadrant angle. Now here's the angle that we're going to, that it makes with the y-axis. So when we swap from coses to sines, we know we're dealing with complementary properties, and we need to think about that angle theta, as I've got it labeled in the diagram, that it's making with the y-axis. So here's the deal. I need to think about how can I align one of the axes. So if I add, subtract beta to it, I can get theta measured with respect to the x-axis, as you can see in that diagram. And it has to be in the second and third quadrants because beta, as we know, is negative. B is a negative value. B is a negative value. B is negative. And for sec of x to equal to a negative value, it would suggest that x would be in quadrant 2 or quadrant 3. So that's why we've set up the diagram like so. Okay, so how do we get this? Okay, relating it back to this picture now, how do we get this angle theta aligned with the x-axis in that way? Well, you can see it's pi on 2 minus beta will get you that fourth quadrant angle. And then, of course, if I go down to here, minus pi into plus beta gets us into the second quadrant, but minus pi into plus, oh yeah, so that's fine. Yeah, okay, and of course, pi on 2 minus beta is, we just take the equivalent angle by adding 2 pi onto it. So three distinct ways from it. I find just working with the complementary properties or the symmetry properties, relating it to sine and cos, and then appreciating that they have an identical form with the reciprocated functions, and then working from there, I find that easier. However, you may enjoy just picturing their placements on the unit circle. So either way, just make sure you understand what to do in these particular questions. All right, this leads us to the final question in the multiple choice section. It's a relation, okay? It's in fact a relation that describes something very close to an ellipse, or you could even say it is an ellipse, but its major axis and minor axis is not aligned parallel with the x or y axes. So it's not something you'd be expected to know, but when you whack it into your CAS, you could actually see it for yourself. There it is. Now what we're told is it's enclosed by a rectangle whose sides are parallel with the axes and just touches the graph at 4 key points. Okay, so what does that mean? It means, so this rectangle, those side lengths of the rectangle represent tangents to the curve where dy dx on the curve is equal to 0. Yep. And these side lengths of the rectangle represents tangents to the curves where dy dx is undefined. We'll just call it is equal to infinity. All right, that's a major part of this question in terms of understanding how to do it. So what does it mean? I need to get an expression for the derivative, dy dx. I need to find out the values of x for which the derivative is undefined. In other words, focus on the denominator part of the function. Of course, this drives this information for this comes from the denominator, and information for this comes from the numerator. We're not really interested in changes in y lengths to work out the width of the box, only the length of the box as indicated. So really, we're going to focus on the denominator function. Now, we're not going to implicitly differentiate this function by hand because we've got our CAS with us after all, and we can go imp diff in our CAS and we immediately get an expression for dy dx. So remember how to do that. So here it is. Our eyes naturally go towards the function in the denominator, and the xy values where that's equal to 0 and the xy values that satisfy the original expression, so in other words ensuring that it's a point on the curve itself, will be the xy coordinates of these points here. So point 1 and point 2. So then we'll have to grab our x values of those points and work out their difference. But that's where we're going. All of this is very, very neatly done with your CAS. There's no point putting in any long-winded algebra. So because of course we could take the rule for the curve, our rule for denominator being equal to 0, solve asking for those xy pairs, and that of course will lead us to points 1 and points 2. Now we're not interested in the y values of those points, only their x values and only the difference of those two x values. So the difference between, that might confuse you a tad. Let me just go back. Okay, that might confuse you a tad. So here's x1 would be over here, x2 over there. So x2 minus x1 gives us the length of the box, and it turns out to be 8.55. All right, welcome to the extended response. So question one, a nice little vector sort of a question, intermingled with some double angle rules, but let's have a look. I think most people got this right. Find the unit vector in the direction of OA and the unit vector in the direction of OB, given by the hat notation. Very easy to do, and hopefully you got those right. Okay, now, interestingly, find the unit vector that bisects AOB. Now, to me, this was interesting because a lot of you got stuck with, okay, so you've got, let's see if I got, all right, maybe I'll just, so OA is of length 5, OA of length 5, OB of length 3, so let's just draw it a little bit shorter. And a lot of you got stuck on this idea of finding the midpoint between, and I understand why, because that became a little bit of our focus. So there was A hat, there's B hat of equal length, B hat, and a lot of you got focused on finding the midpoint of the direct line between A dash, we'll call it, and B dash. Okay, now of course that is a bisector, but of course any multiple of that vector will also be a bisector of AOB, and that's all we're really after. So at the end of the day, rather than finding specifically that point that bisects A dash and B sec, the midpoint of A dash and B dash, all we really need to do is just add A hat and B hat together. So let's just A hat and B hat together. And we know we're going to be dealing with some position vector that bisects AOB. So let's just quickly bring up the solutions. And that's all I need. That's all I'm doing here. So the sum of the two leads us to a vector of a particular length that happens to bisect AOB. That's great, because the advantage of actually factoring out as I have 2 on 15 means I can just focus on these nice integer values, and I can focus on a vector that's a multiple of 2i plus 5j minus 11k that's of unit length. So what I'm going to do is work out what is the magnitude of 2i plus 5j minus 11k. I square them and sum them. So let's just get back into this. I square them and sum them. Here it is. Turns out to be a nice value of 150, as it turns out. So the unit vector that bisects AOB is simply determined as the sum of the unit vectors A and B, and the unit vector of that. So, and that's what I achieve by putting it into that sort of a form. Then, of course, it just collapses nicely, being 150 being a nice number, and whether you rationalize it or not didn't really matter. All right, so that's it. A lot of you were overcomplicating this, and that's, if I can impart anything, it's just understand that basic principle. Okay, these should have been absolute gimme questions, really. Just here's some extra points. So it was a bit surprising why it wasn't the case. Find the scalar resolute of OA in the direction of OB. The scalar resolute, not the vector resolute. Some of you were calculating, and that's simply it. It's OH, so OA dot product with the unit vector in the direction of OB. That's it. There it is. And so it was just a super easy dot product divided by the magnitude of OB, which you'd already calculated, which turns onto 5 on 3. What does that mean in terms of the situation? Now here's a diagram, a helpful diagram. OA of length 5, OB of length 3. That scalar resolute is simply that length there. That's the scalar resolute. That is the length OY, as you can see in the diagram. please understand what you're getting with these vector resolutes. So, okay, so we're asked to work out the cosine of angle AOB. So in other words, the cosine of that angle in there, and of course it's just adjacent, which is your scalar resolute, we've just worked out, divided by the magnitude of A, it's equal to 1/3. Okay, nothing terribly hard about this. All right, now this was a question not too dissimilar to what we've done in class. So now I thought I'd just take a snippet of that little diagram. Use an appropriate double angle rule for length OX. Now we know that this OX bisects the two. So if we know cos of 2 theta is equal to 1/3, we need to find out what is cos of theta. Why? What is cos of 1 theta? Because we already know the adjacent side length in that triangle is the scalar resolute that we calculated previously, 5/3. And if we know what cos of that angle is, we're able to work out OX, because the relationship between theta and OX and OY is adjacent and hypotenuse. So all right, good. So off we go. We know that cos of 2 theta is equal to 1/3. So what will cos of theta be equal to? All right, so there it is. So we've got rearranging plus or minus, but we're only going to take the positive since theta is an acute value. And then it's just simply subbing in those values. Cos of 2 theta is 1/3. 1/3 plus 1 divided by 2 square root is the square root of 2/3, or root 3/6. And then how do we calculate OX from there? It's just SOHCAHTOA, that's all it is. So cos of angle XOB will be OY on OX, rearranging to make OX the subject, and I've rationalized the denominator, not that you really have to, but you come down to 5/6 on 6. So that's the length of OX. That's important to appreciate for this next part, because on this next part, we need to calculate what is the vector OX. Now, I thought this was quite a neat little question. We know the length of OX. We know the unit vector that bisects OA and OB. So of course, it's a vector of length 1 in the direction of OX. So we can customize the length to match that of OX by just simply multiplying it by the length of OX, and there we go. We get to that nice simple expression. I thought that was pretty neat. But please, hopefully you're seeing nothing was really super tricky in all of that. Okay, so question 2 began with a sec function. So it was a sec function that had been dilated by 3 from the x, 2 from the y, and translated downwards 3. Okay, define D, define its maximal domain using a parameter ranging over Z. Now that was there to be helpful. Obviously it made a roguish appearance in SAC1, the previous SAC by mistake, and didn't lead to too much confusion, but obviously confused the question somewhat. But here it has an appropriate place. All right, so let's think about that. It's been dilated by a factor of 3, so that's not going to affect the domain. It's going to be translated downwards 3. That's not going to affect the domain of sec. But it will be dilated by a factor of 2 from the y, and that will affect our expression of the maximal domain. So let's just have a look at that. So here is what we know to be all the asymptotes of the sec graph. So cos of pi on 2 is equal to 0. So the sec graph has an asymptote at pi on 2, and they're all separated by half the period. So if I add k lots of pi to pi on 2, it's an expression that covers all possible vertical asymptotes for the sec graph. Now, because it has been dilated by 2 from the y, I can just multiply each of those by 2, and it gives me an expression for all the asymptotes of this particular function f. And then I can express it as the reals, except for all of those points k is an element of z. All right, now most of you didn't know what to do with that question, but think about it. It was a test of your ability to express something mathematically in the language of maths. So I thought it was quite nice. Okay. All right, so let's keep going on to the second part. That was done well. It's just a simple application of the chain rule. So sec, just make it cos the function to the power of -1. Applying the cosine rule leads neatly to the form of the answer required. All right, now this question broke my heart, I've got to tell you. Show that f dash is 1 when x is equal to this or x is equal to that. Show that means you can't use these values in your answer. I don't know how many of you were just subbing in f dash pi on 3 plus 4k pi, yada yada, showing that equals 1 for any integer value k. Nice. But it's not what the question was after, and unfortunately for all of those who did such a move, you didn't get any reward for it. So show that, show that, show that. Prove, show that means you can't touch your answers. The only reason why you're given answers is to help you with the next or subsequent parts. All right, so it's all about equation solving. We take our expression for f dash of x, we set it equal to 1, we multiply out the denominator, and we've got this equation to solve. Sine of 3 x on 2 equals 2 lots of cos squared x on 2. How do I solve that equation? Well, those onto it realize, well, it's just Pythagorean identity, and then you've got a hidden quadratic involving sine x on 2. Okay, making it equal to a brings it into relief nicely. You get two solutions for sine x on 2, 1/2 and -2. Obviously, -2 is not a sense. Well, no solutions emerge from it, and then off we go with sine x on 2 equals 1/2 and solve that. Provide a general solution for that is what it's all about. So obviously pi on 6, 5 pi on 6, solving for x on 2, pi on 3, 5 pi on 3, the period of the function is 4 pi, and hence the form as required. Okay, good. Okay, there's a bit of a blurb in the beginning that possibly should have come after part D. But here it is coming before part D. G is the same function, but just a part of it, only from minus pi on 3 to positive pi on 3, just a section of it. Onto the endpoint of that function G in the first quadrant, a section of translated inverse sine curve is smoothly joined. Okay, a smooth join concerns a continuous hybrid function that approaches the same gradient at the point of connection. Okay, there we go. Now, in the previous part, you've worked out, because it's a member of the general form, at x equals plus or minus pi on 3, g of x will have a gradient of 1. Okay, that's what we established before, and that's the significance of that. But part D is really unrelated to all of that understanding. It only comes in later. Show that the derivative of the inverse sine graph is equal to 1 only at the origin. Okay, so there we go. We differentiate. That was a fairly easy task. Pretty much a gift for 2 marks. You got 1 for setting up the rule for the derivative of inverse sine, and then going on to show that it can only occur at x equals 0. What's the significance of that? It means it's only, so here's our inverse sine graph. Okay, it means only the section. Actually, let's just grab, it's only this section here from x equals to 0 up to x equals 1, or it's only that part of the sine graph we're going to tack onto the end of our g of x function so that it has a smooth join. So that becomes relevant for where we're going. Okay, so this is the section of our inverse sine graph that we're going to add onto our g of x at x equals pi on 3. Okay, and it's going to be that smooth join, so it's going to share a gradient of 1 at that point, okay? And we know that, let's have a look at the form of inverse sine graph. So it's the standard inverse sine. There are no dilations. There's no dilations from the x, there's no dilations from the y. It's only a translated function, which means at the midpoint of this inverse sine graph is where, so that's equal to 1 at the midpoint, we'll just say, as it is for just a set, because it's the standard inverse sine graph which has a gradient of 1 at its midpoint at the origin. It's just been translated b units to the right and c units up. So it's a case of appreciating what are b units. So it's that. So it's got to be translated pi on 3 to the right and a certain value c upwards. So that's what it was all about. So how do I work at that c value? Well, of course, I've got to evaluate the function at pi on 3. I've done it by hand, but of course you've got your cas. You could just work it into your cas. And so here's the translation matrix. So we're taking our inverse sine graph, our basic inverse sine graph, moving it pi on 3 to the right, and the value we've calculated is the value of g at pi on 3, that was upwards, and then we've got our smooth connection. Okay, so look, some of you maybe missed the connections of this with the earlier parts. Always think backwards to how do the previous parts relate to this part. And last but not least, there's also a function, an inverse sine function, smoothly joined on to g in the negative direction, and of course it's just simply taking your answer to the previous part and where you see x, changing it to minus x, and that's what I would have accepted. Either form, of course, because the inverse sine function is an odd function, I can just factor that negative out the front, which just makes it look a little neater, but that was it for your 1 mark there. Okay, so question 3 was a complex numbers question. If you'd practice your past SACs, you would have seen that would have been helpful, I'd imagine, because there was a lot of similarity between some of the past SACs and this sort of a question. It began fairly gently with the sketching of a couple of rays. So I was looking for, here's the first one. Let me just grab the pen. Here's the first one. It's all complex numbers with an argument of 2 pi and 3. So we're looking for that open circle at the origin, moving off in an appropriate direction off into the second quadrant. The second one was dealing with all complex numbers with an argument of, well, after a translation, has an argument of pi on 3. So I'm looking for a ray that is sloped at 30 degrees, roughly 30 degrees to the positive real z direction. If it was marked, that was nice, but I guess I didn't take off marks if it wasn't. But some of you maybe had trouble locating the starting point, and of course, it's always useful to 3 plus z plus 3 minus root 3i is to rearrange it as z minus a complex number, and that leads directly to the, let's go back, sorry. So z minus, okay, z minus 3 plus root 3i, and that clearly indicates the location of the translated start of your ray. All right, moving on to part B. Let's just click along here. Okay, we're told to make O the origin naturally and let A be the point minus 3 root 3. Aha, so it's the starting point of that second ray that we just discussed. So let me just get a pen. And okay, so this here will be our A. Okay, and we need to describe that in polar form with principal argument. So there you can see I'm setting up that triangle. So root 3 up, vertical, a run of 3, a rise of root 3, angled in the negative real z direction, giving us 30 degrees. So obviously, the angle measured from the positive real z direction will be 150 degrees, or 5 pi and 6. And of course, working out its magnitude is easy enough. It's root 3 squared plus 3 squared, making it 12. Root 12 is 2 root 3. So pretty easy way to pick up 2 marks. Some of you are even dropping marks there, which was disappointing. So, all right, so that is point A in principal argument form. and point A is the start, albeit not inclusive, in the second of our two rays that we had sketched above. Okay, so I thought this was pretty neat. A lot of you weren't sure what to do. So we're now going to talk about P being the set of all complex numbers marked by the first ray, the ray open circle at the origin, and Q be the set of all complex numbers marked by the second ray, the ray oriented at 30 degrees with respect to the positive real z-axis that had been translated to point A, we'll call it. Okay, so obviously if P is some, sorry, P isn't the set, P is a member of the first set and Q is a member of the second set. So it's some member of that set. So a point P, OP, for the first ray is a vector aligned with the first ray, but a vector of length 1, and it'll have that description nicely. And AQ is a vector from point A to some point that lies on the ray. So it's obviously not equal to A because Q can't be equal to A. If we convert that to a unit vector, we're dealing with that simple expression. So I thought that was a neat way to describe a unit vector in the direction of OP and AQ using the arguments that were given in the setup of the rays. But use an appropriate compound angle rule to show that those unit vectors are perpendicular to each other, and therefore, in other words, that the two rays are also crossing at 90 degrees. But this is what you would do. It was just hoping to multiply your I components together, multiplying your J components together, and let's see if I've got my pen operative. There it is. Okay, and then working backwards with the compound angle rule and evaluating cos of pi and 2 to be equal to 0. So that's what I was really looking for in that question. So if you're not sure what that information means, you really try to read it carefully and try to understand what this information is giving to you. All right, moving on to the second part. Hence show. I don't think many of you at all got this correct. So using the fact, so let's just go back to our Cartesian plane or our complex plane. So here's O, okay, that's our first array. Here's our second ray. Okay, there's point A, there's point O. And what this information suggests is that it's 90 degrees. So because we were dealing with unit vectors, it didn't really matter the length, but because their dot product is equal to 0, let's just call that point of intersection X, and that's the point minus 3 root 3. They're crossing at right degrees. So that was the hence, is appreciating that the two rays are intersecting at 90 degrees, and that comes directly from the above information. Okay, so hopefully if you're not sure about that, follow it up with me. Hence show that the intersection of the complex numbers that makes up the first ray and the complex numbers that make up the second ray is equal to 3 cis 2 pi and 3. So let's just go to that little diagram I've drawn. So in other words, X is that point of intersection, but we need to show that the distance of X from the origin is equal to 3, and the angle of rotation, of course, will have to be 2 pi and 3, because it's a point. A point of intersection is, of course, a point that lies on both of the two rays, and every point that lies on the first ray has an argument of 2 pi and 3. So really, this is coming down to proving that it has a magnitude of 3. So how can I do that? You can see what I'm doing over here. I'm working with a right angle triangle, and that's the hence part. So using the fact that they're intersecting at right angles, I'm able to work out the distance of point A from the origin. Okay, it's equal to 2 root 3. X gives me the magnitude of that point, and I can clearly state that if it was 120 degrees or 2 pi and 3 from the positive real z-axis to the first ray. We've already calculated that to be 30 degrees. It's easy to establish that 30 degrees must be the angle between the two, the line to point A and the line to point X from the origin must be, so AOX must have an angle of 30 degrees. Okay, and again, there it is, SOHCAHTOA. So cos in this case relating hypotenuse to adjacent, and we're able to show that it has a value of 3. And we know it's almost by default that it has an argument of 2 pi and 3 because it's a point in common to both rays, and every point along one ray has an argument of 2 pi and 3, so it too must share that property. Okay, the first part should have been a no-brainer. Okay, convert 3 cis 2 pi and 3, which is that point in common to both rays, to Cartesian form. So hopefully you guys can evaluate what is cos 2 pi and 3, what is sine 2 pi and 3 easily enough. It turns out to be that. Hence, so using that Cartesian form, there's that hence again. Using that Cartesian form, show that it's going to be a member, show that this is true. So all I do is I replace 3 cos 2 pi and 3 with the Cartesian form, collect your i's and j's, and then it's easy enough to show that the modulus of that that complex number in Cartesian form is equal to root 3, and so it satisfies that condition. Okay, things were getting a little bit tricky now at this point, I would have thought. So T is a set of all complex numbers whose distance from -3 plus root 3i, which of course we should start to identify now as point A, is fixed at root 3. All right, now, firstly, it's a circle. It's a circle centered at -3, root 3. So that's the first part. Now, this next part of my marking criteria, that it's sandwiched between the radial lines 2 pi and 3 and pi and 3, I was less fussy about, so long as it wasn't too far out of those two radial lines. I gave you full marks for that. But here's the thinking behind why it is. Okay, so I did ask you to label cis 2 pi and 3 on the circle, and the aim was to show, building up all that understanding, is because this is representing point A. I think I've just drawn it slightly out of whack. So we know that they run tangent, the line from point A, which is the center of this circle, hits the line from the origin with a radial value of 2 pi and 3 at right angles. Okay, that's stuff we've already built up already. So here's the origin, and here's that common point, 2 cis 2 pi and 3. Now, because of the fact that that's a point on the circle, and because of the fact that the line from the origin to that point runs perpendicular to the line from the center of the circle to that point, it must mean that that point is on the tangent line that it runs along the radial line 2 pi and 3. So that it must be on the tangent line. So let's just call that point X. So we know the length of O to X is equal to 3. We know that this angle in here is equal to 30 degrees. So the line from the origin to the other end of the circle, okay, must meet it at -3, because what we're dealing with a unit circle. Okay, hang on, I'm just having trouble with my marker. So at the end of the day, we know if O is an external point and I've got a circle, I draw the line from the external point to a point on the circle will be the same in length as the line from the external point to another point on the circle. They must be the same in length. And in fact, if I think about joining it up to the center of the circle, let's just call it O dash dash, it creates two congruent right angle triangles. Okay, so that's a geometric fact that you'll have equipped at you. So in fact, this means ultimately that if the line with argument, so the ray with argument 2 pi on 3, if that's a tangent to the circle, which we can safely say it is, and the line that hits from the origin through the center of the circle is 5 pi on 6, so 2 pi on 3 plus pi on 6, then a further pi on 6 further around will create another tangent to the circle. So moving another pi on 6 further around creates the radial line pi. So the radial line that we get by that marks the negative real z-axis. So of course that length here must also be equal to 3, bringing in our geometric understanding. So another member of T with a modulus of 3, the only other member on the circle with a distance of 3 from the origin is the point where the radial line along the x-axis touches it at a singular point, and that's at -3. So hopefully I've done a bit of a hatchet job trying to explain that, perhaps, but that would have been the thinking behind why -3 must be a member of T with a modulus of 3. So perhaps some of you even drew it and just subbed in -3 to see it, or you might have just noticed from the form of the equation of the circle that when you remove the negative component, you're left with just an imaginary number that has the same magnitude as root 3. Either way you got it, I was thinking about it from that geometric perspective. Hopefully you can see it now. Please ask questions if you'd like that further clarified. Yeah, but anyway, it was a reasonable challenge, that sort of a question. All right, now this was one of the trickier questions on the paper. So let's see if you can follow the discussion as we go through this. So we're told A and B are members of T, in other words, they're points on the circle. We're also told that the distance between A and B is equal to 2 root 3. Now that's significant. So firstly, appreciate that's describing the distance between A and B. We know that the radius of the circle is equal to root 3. So what must be the relationship between A and B? They must be, so the line from A to B must be the diameter, must represent a diameter of the circle, because we know that the circle has a radius of root 3. So if the distance between A and B, 2 points on the circle, is 2 times that radius, we know that the line segment AB must represent a diameter on the circle. Interesting. Okay, let's move on to the second bit of information. We're told the set of all complex numbers whose distance from A is equal to the distance from B. Straight away, you should be thinking perpendicular bisector is defined by that equation. So the equation of that line, what do? We're dealing with the polar understanding of complex numbers. So we need to think about the angle of rotation that represents from the positive real z-axis. We know the gradient is equal to the inverse tan, will be equal to, theta, my bad. Theta is equal to the inverse tan of -1 on root 3, which leads us to minus pi on 6 or 5 pi on 6. So we're talking about a line whose angle of rotation from the positive real axis is minus pi on 6 or equivalently pi on 3. In other words, it's a line that cuts through the center of the circle. Now that leads us to the diagram. So A and B are points on the circle where the line segment between them is a diameter. The second thing is the line through the center of the circle is a perpendicular bisector of that line segment AB. So hence the circle. Now, the only thing confusing I can see about my diagram is that I've labeled the center of the circle C and the point representing representing the complex number A as capital A. Now, previously I called the center of the circle A, so don't get confused by it. Just run with this particular diagram. Okay, so we're going to extract out the right angle triangle ACO. Okay, now of course AO, take careful note of that. AO is not a tangent, but it's a line that cuts through the circle. It's a secant. It cuts through the circle. Let's just add a couple of points. So it's the direct distance from A to O, but it's the length we need to describe. I'm not sure why I've got that labeled R then. Okay, let's just call that X. Okay, so that length I need to find, because that length of AO will give rise to the R, the modulus of the complex number A that I need to find, and then ultimately I need to work out its angle of rotation from the positive real Z form, from the positive real axis, in terms of the given form that you can see in the question. Okay, so AC, according to that diagram, of course, will be equal to the radius of the circle, which is equal to √3. The distance from O to C, the center of the circle, as we've already established, is equal to 2√3. Yes, that's right. That's what we established that from a previous part. Therefore, AO is, oh no, there it is. There's the length of OC calculated. Okay, so therefore, AO is just quite simply obtained via Pythagoras. So let's just clear off some of that workings out for your benefit there. Okay, so, and we arrive at a value of √15. Okay, let's just pull that out. So we're just working with Pythagoras there. √3 squared plus 2√3 squared square root, and we therefore have the modulus of the point A. So the distance of A from O will of course be exactly the same as the distance from B to O. Why? Because OBC is a congruent triangle to OAC, exactly the same triangle, but reflected about that line, y equals -1 on √3x. All right, so what about the argument? Of course, we can work out theta quite nicely, and of course that'll be equal to, the theta will be the same angle as COB as COA is, and that's, why not just use our inverse tan to work that out? We've got access to the length AC, access to the length OC, so the inverse tan will be equal to 1/2. So in other words, we can describe the angle of rotation from the positive real Z axis to OA as the angle of rotation to OC plus inverse tan 1/2, taking us to point A, and 5π6 minus inverse tan 1/2, taking us to point B. Okay, so there's our A's and B's described in the form set out. That was a tough question. I think some of you got it from memory, but obviously not many. There were some challenges involved in that complex numbers question, no doubt. Okay, question 4 was absolutely one of my favorite questions I've ever come up with, I must say. It just linked through the course quite nicely. I thought, I'm not sure if you guys were fans of it or not, but let me just go through it with you now. Okay, so it starts off like a geometric proof kind of a question. Here's a general rhombus. We're told that OA and OB are defined by vector variables A and B. It even says that it's a special case of a parallelogram, which it is, to give you a bit of a hint. The first part was done really quite well. A lot of you sort of can recall this pathway towards a proof involving the dot product. Showed that the diagonals in a rhombus will always be perpendicular. I think you did this really quite well. So OC is A plus B. So vectors A plus vectors B. AB could be B minus A. Fantastic. The dot product, difference of two squares. Okay, coming up with the dot product of a vector with itself is that link towards magnitude, and it being a rhombus by definition, it means that those magnitudes are the same, hence the dot product is equal to 0 is what I was after. So I think a lot of you did get 2 out of 2 for that part, which was pleasing to see. Okay, the second part was actually quite surprisingly not done very well, even though that it did feature in the textbook. It's possibly even one we went through in class. But really, I would have thought it was one of the earlier questions in the exercise on geometric proof. So I'm a bit surprised not more of you did well on this one. Okay, so here's one approach we're going to take. Let M1, so OC we've identified to be a diagonal. Let M1 be its midpoint. So easy enough, straight out calculation. The position vector to M1 could be described as follows. Let M2 be the midpoint of AB. So we're not making any assumptions that M1 and M2 are the same at this particular point. So M2 will be half of AB, which is half of AB. But this enables us to talk about its position vector from O to M2 is OA plus AM2, which is equal to half A plus B. Now that turned out to be exactly the same position vector to M1. And that will only ever be the case if those 2 points represent the same point. So OM1 and OM2 are the same. So the midpoints are the same, hence they bisect each other. Lovely. Okay, let's just get rid of that because I need to bring in something else. Okay, so here's another, let's just bring in, here's an alternative way. You could have brought in something like the uniqueness property as well. So let M be the point of intersection. This time we're focusing on the point of intersection. And so we're saying OM will be some scalar multiple of OC. Okay, AM will be some scalar multiple of AB. And again, we can get, from there, we can get an expression for OM either indirectly or directly via the collinearity property, but there it is. And then it's a case of equating parts. So 1 minus beta is equal to alpha. Beta and alpha must be the same. And it leads to the only conclusion that alpha and beta is equal to 1/2, and hence we've proven that the diagonals bisect each other. So choose whatever approach that you like. All right, so this question started fairly gently. So again, it's all about the rhombus. So this time we get a rhombus form when we link OA, AB, BC, and CO together via line segments. Okay, you can easily confirm the side length in each case is equal to 2. Now, gentle enough, we need to work out C, this point here, and A is complex numbers in polar form. Easy enough to work out. It has a distance of 2 from the origin. C is an angle of rotation of pi on 6. A is an angle of rotation of pi on 3, 60 degrees. Now, I've got to apologize for part D. Using area A equals half BC sine A showed that the area of OAB is 1. I was actually intending OAC. Showed that the area of OAC is 1, and hence the area of OABC is equal to 2. So really it was meant to be just a gentle little question. Okay, it's easy enough to show that the angle between them is equal to 30 degrees over here. And each of length 2. And it was a simple matter of showing that that was had it filled up an area of 1, and therefore it being a rhombus, that triangle would have been congruent to it, and so the area of the rhombus is 2 triangles of area 1, making it a quadrilateral of area 2. And you can see that's what I'm doing here in the formula. However, as stated in the question, it was referring to OAB, not OAC, which is a bit annoying, isn't it, folks? So let's just think about how that would work. A little bit more complicated, but still, end of the day, it's the same thing, showing that green triangle has an area of 1 is a little bit more complicated, but still not too bad. What you'd need to do is show line OB is obviously 60 degrees with respect to the positive real z-axis, if I draw a line from A running horizontal with the real z-axis, obviously that's going to be equal to 120 degrees, it being co-interior. The angle it's making, AB, is making angle of 30 degrees, so the internal angle would be 150 degrees. So the calculation therefore would be half times still 2 times 2 times sine of 150, turning out to be exactly the same value as you'd have it before, but involving far greater thinking, and it's not what I intended with the question, so I apologize that I didn't proofread that more carefully. Some of you did that without actually reading the question carefully enough, and I gave you full marks for that. So, okay, continuing on. All right, find an A such that if I take U, so what is U again? So U is a complex number to C, so let's just get rid of all of that junk here. Okay. Okay, so here's our U vector. Okay, and if because OC is the same distance, here's our V. Because U and V have the same magnitude and the angle between them is equal to 30 degrees or pi on 6, then clearly if I just take U and multiply it by a complex number of magnitude 1, but with an argument of pi on 6, I'll be easily able to rotate U onto V. So that was the intention of that question. Okay, state point B as a complex number on the complex plane in terms of U and A only. So B is could be OA plus AB. So let's just highlight AB. Now AB is exactly the same vector as OC. So really this is vector V plus U. What is V after all? V is equal to U times A plus U, which you could write like that, or you could factor out the U and write it in the form that you see. Okay, so hopefully that was okay. Okay, so moving on. This was quite a nice question, I thought. We're describing a set of complex numbers, a locus of complex numbers in this way. M, of course, is the midpoint of OB and OC. So let me just get a pen. So an M, lowercase m, is the complex number form of it. Capital M is the coordinate pair of it. So that's just a way to make that distinction. So we're told the set of all complex numbers where Z minus M times the conjugate of we need reduces to the distance, the set of all complex numbers whose distance from M is equal to root 2. In other words, a circle centered at M of radius root 2. Now, you're not meant to replace Z with X plus IY. I was originally going down that path and thought, why not look at the conjugate properties as a neater way of getting there. So of course, how do we go about that? Conjugate of Z, so just focusing on this, conjugate of Z minus conjugate of M is equivalent to Z minus M conjugate. Okay, so it means that in this product, we could reduce it to that sort of form. And then this brings in another property to say a complex number times by its conjugate will always be equal to its modulus squared. We take the square root, no negative, because modulus is always positive, and we arrive at the form we need to. Lovely. Okay, moving on to the next part. Okay, ignore those annotations. I'll come in as relevant later in the question. So find the y-intercepts and the x-intercepts of the circle on the plane effectively. In the words of complex numbers, find the imaginary numbers. Imaginary numbers are complex numbers with zero real component, and real numbers, of course, are complex numbers with zero imaginary component. So, yep. So find the x-intercepts and y-intercepts of the circle. Okay. So this should have been. Let's just make sure I've got the pen. Yes. So really, you had use of your CAS. So what is M? So M was the circle, the midpoint of the A and C, and in fact the same. So that was your M value, and we know we're talking about a circle of radius 2 from that point, so we know it has that Cartesian expression, so that's what I was looking for. And then you've got use of your CAS, so you just let x equals 0 solve for y, let y equals 0 solve for x, and of course your y values refer to imaginary numbers and your x values refer to real numbers. Some of you gave them as coordinate pairs, and that was perfectly fine as well. All right, part I was a late inclusion. I thought this would help. So it would show that sine 15 degrees is equal to that. And really, I would have thought this was a bit of a gift of a mark, but some of you did all kinds of obscure things at this point. Just always be on the lookout for those 15 degrees or pi and 12s. The compound angle rules are always the way to go. But you get to that expression through an appropriate use of the compound rule. Okay, now what's the point of that in the context of this question? Well, here it is. Find the proportion of members of S with positive real and positive imaginary components. In other words, find the proportion of the circle in the first quadrant. Now, if you look at the picture, it looks like quite a vast majority of it lies in the first quadrant, but this is the way to do it. So we know the x-intercepts, y-intercepts are the same. So let's just focus on this triangle over here. Okay, now it's an isosceles triangle. Its base is, as you can see, root 3 minus 1. And it being an isosceles triangle means we can split it into two identical congruent right angle triangles, as you can see there. So that's why it's theta on 2. Now we're talking about a circle of radius 2, hence that's radius 2. And I'm taking half of that distance between intercepts is root 3 minus 1. What's the relationship between them? It's sine. There it is, SOHCAHTOA again. And I've got sine theta on 2 is equal to root 3 minus 1 on 2 root 2. Lo and behold, there's a match between the previous answer. Therefore, theta on 2 is equal to 15 degrees. Theta is equal to, therefore, 30 degrees. And that's huge. That means the proportion of the circumference that lies outside the 2 will be 2 lots of 30 degrees, in other words 60 degrees, out of a total rotation of 360 degrees. So 300 degrees out of 360 degrees reduces to a nice neat proportion of 5/6 of the circle that lies inside the first quadrant. There it is, geometry at work. Don't you love it? Okay, we're getting near the end of the paper now. So T is the set of all complex numbers along the side lengths of the rhombus OABC. So there it is on the plane. Consider the 5 loci, all related to that set of complex numbers. Just defined collectively as S to the n equals W times cis pi on 3 to the power of n, where W is any member from the set T of complex in the rhombus OABC, and n, that power can range anywhere from power of 1, 2, 3, 4 up to 5. So in other words, we're taking W, members of the complex number, and multiplying each member by cis pi on 3 for the first set S1, multiplying it by 2 pi on 3 for the second one, 3 pi on 3 for the third one, 4 pi on 3 for the fourth one, and 5 pi on 3 for the fifth one. And what does it mean to take a set of complex numbers and multiply them by a fixed complex number of modulus 1 and of a particular argument? We take each member of that set and perform a rotation of pi on 3 or 60 degrees. So, so in terms of the grid that you're given, this is what I was hoping to see. You're hoping to see each radial line represents an increment of pi on 6. So OA gets rotated two sections through the polar grid. That becomes the image of OA under the first set of rotation. That's taking each member of OABC and multiplying by cis pi on 3, going through 2 rotations until you get the first. Once you've seen that, the rest just follow naturally. So let me just remove my markings from this very pretty picture, I think. Okay, so getting back to this, so the first S1 is by rotating OABC by pi on 3, the second one by 2 pi on 3. So they all move 2 radial lines across effectively, and that's what I was looking for. I think you'd agree that's quite a pretty picture, and you got 2 marks for picking up on that pattern. Okay, the second part was find the total area. So you can see we knew that the area, actually no, sorry, I brought that up too quickly, but that's all right, I'll just leave that there for now. We know that the area of OABC was equal to 2 units squared, 2 square units. And of course that area won't change. We're not extending it, we're not enlarging that shape, as we're just simply taking that shape and performing a rotation of 60 degrees anti-clockwise each time. So the area remains fixed. So we've got 1, 2, 3, 4, 5. 5 lots of 2 is 10, and that's what I was after for the answer. Now the last, quite a few of you were onto it, but you didn't answer the question as I would have liked. A lot of you linked this question to the previous one and were working out the total area, and you did it correctly, but the question itself was find the area of a single one of these P subscript I, well, P subscript N for a given value of N. So how does this relate to the previous one? Well, the only difference is rather than taking every member of our T being a complex number along the rhombus OABC and multiplying it by cis pi on 3, multiples of cis pi on 3, we're taking it multiplying it by multiples of 2 cis pi on 3. Aha. So not only does it rotate each member, but it makes it 2 units further away from the origin. So if each length corresponds to 2 times the previous length, so basically this is what it now would be. So this would be P1. Okay, so corresponding side lengths are twice their previous value, which means that the area that this relates to, so if this had an area of 2, this has an area of, because each length has been doubled, and area is obviously in this calculation is a length by width, or diagonal by diagonal divided by half. It'll be increased, so that's the original area increased by a factor of 2 squared. So that becomes the area of the first one, and then for that one, its area is of course increased also by a further 2 squared, and then 2 squared on it's multiplied. So it's the scale factor that takes you from the area of one to the area of the next. So this relationship between the first rhombus, OABC, between OABC and the first rhombus that you get under this operation will look as follows, but obviously after that it's too big to represent on the plane. I've got to think more abstractly about it, and then you've got this this geometric sequence occurring for P1 to P2 to P3, and I just wanted you to narrow it down. So what would be the area of Pn for any member along this sequence where there's 5 members of the sequence, so P1, P2, P3, P4, P5, and you could come up with a general rule from there as Pn, so it's 2 times 2 to the power of 2n or 2 to the power of 1 plus 2n. That was designed to be a really tough question. And I think no one got it. However, a few of you were onto the pattern, but then didn't read the question carefully enough and realized it was just a general expression for each individual Pn rather than the sum total of the Pn that you got because you were linking it to the previous part. Nevertheless, food for thought, a good little question to think about in future. Okay, and final page. No, almost. We're almost there, thank goodness. It's been exhausting sitting through this and trying to explain every question in detail. Please follow it up with any questions you may continue to have. All right, so now, finally, the last little cherry on top is this idea of linking O to A and A to B, O to C and C to B with either sections of the sine graph or inverse sine graph. Okay, so let's have a read of it. So we're told that the sine curve that connects A and B, so it's a sine curve that connects A and B, let's just highlight that, is of that particular form. So that you can see that there's been no dilation from the x-axis, but it has been dilated, it's been stretched from the y-axis, and it's also been translated. And you're told that it's a transformation of basically the first part of the sine curve from 0 to pi on 2. So there's pi on 2, starts at 0, 0, so it's a transformation of that curve leading to the curve that you see before you. So we need to find what those values of A, B, and C are for that to be possible. Okay, so first things first is we could think about, you know, the stretch involved to go from A to B. So this is obviously a quarter of a period, and so the stretch from x equals 1 to x equals 1 plus root 3 covers a length of root 3, so hence the period of this function is equal to 4 root 3. So again, we can do our calculate. What must be the coefficient of x? It must be 2 pi divided by 4 root 3. It must be pi on 2 root 3. So that gives us immediate access to our A value up there. Okay. Now, what sort of translation has gone on in this particular setup? So let's just grab a different color. It's been moved 1 across from the origin. So here it was starting at the origin. We're going to move 1 across. Whoops. 1 across. Whoops. And root 3 up. So we're going to take that curve, shift it 1 across, root 3 up. We're also going to perform a dilation to it given by this factor. So at the end of the day, let's see if I've got the solutions nicely for you. If not, I'll annotate it. Okay, at the end of the day, there it is. We can write it as in this form, in standard function form. Here's the clear dilation factor from the y-axis. Here's the translation pair, 1 to the right, root 3 up. And then, of course, you need to multiply through to put it in the form required by the question. So A is equal to this, as we discussed. C is equal to that, but B is, of course, minus 1 times your A factor. Okay, hopefully that's clear enough. Okay, the curve BC is a reflection of the curve BA about the line segment OB. Of course, the line segment OB is a line segment along the line y equals x. So we're talking about BC must be the inverse function of BA. Okay, so we've already got the rule for BA. So how do we come up with the inverse function? We swap our x's and y's, and then we go through the process of making y the subject. So you can see that's what we're doing over there in the set of working out. Now it's legitimate that it's describable as an inverse sine function because we're told that BC ultimately, so BC was ultimately a transformation of that part of the sine curve from 0 to pi on 2. And as we know, that section of the curve is part of the behind the scenes definition of your inverse sine graph. So there was no need to account for anything else in our thinking. It was still all relatable to our standard definition of your inverse sine graph. So all good to just perform inverse operations, not a problem at all. leading to that final form. Okay, the final question, and surprisingly, a few of you got this, which was quite a nice to see. So this was the way to think about it. Well, one of the ways, I guess. Okay, so we needed to think about the area that that particular shape encloses, and relating it to our understanding of a rhombus. We know a rhombus means that the diagonals cut at midpoints and at right angles, which means we can enclose it nicely in a box or a rectangle. A rectangle whose width is equal to the distance from A to C, which as it turns out to be root 3 minus 1 root 2. There was C, and whose length was equivalent to the length from O to B. Okay, so we can enclose it in such a box, but when we do so, you can see you'll get this lovely case where this area in here is matching. So in each of the 4 segments that those AC and OB lines break up, we're going to get it's going to take up half of the area of the overall area of the rectangle, and you can see that via the symmetry there that I've tried to highlight in that picture. So at the end of the day, we're going to calculate the area enclosed via that understanding. So the area enclosed will be equal to the area of the rectangle divided by 2. Nice little calculation, turns out to be equal to 2, and neat. So the area enclosed by that shape is equal to the area of our original rhombus, which would have been another way you could have thought about determining the area of this particular shape as well. All right, so some of you may have thought even about the direct line segments between the two. Is the area outside, the area below, is cancelling each other out, and you're back to the area of the rhombus itself. So nice. Okay, well done. It was a tough SAC. The key is to learn from it. The key is to grow from it and to gain some understanding and a bit of insight into some problem solving. Hopefully you have. Please follow up any questions that you may have had with me, and we'll talk shortly. Bye.